Hey everyone, welcome to our fourth week of HPC in the cloud. I'm Joe Schoonover from Fluid Numerics, and today we're going to be talking about Python package management strategies, particularly on HPC clusters. Since we're now in the day and age where just about anyone can click to deploy an HPC cluster, I think more people are starting to take on some additional roles, including managing their own packages and software dependencies. So we figured this would be relevant for software developers and system administrators who are looking for different strategies to handle Python packages. If you're going to follow along with the demonstration today, we're going to be using a cloud-native HPC cluster on Google Cloud. And to get started, if you wanted to use that same cluster and just follow along with what I'm doing here, go to console.cloud.google.com and create an account if you don't already have one. This will basically set you up with some trial credits if this is your first time signing up, so that you can get through some of the tutorials today. So I guess real quick, I'll give you a little bit of a brief walkthrough of how to create that cluster in case you did miss our live streams from a couple weeks ago. I highly encourage you to check out those videos. They're still posted up online to get you through the creation process for creating that cluster. Of course, you can also check out our documentation at help.fluidnumerics.com/slurmgcp. So I guess I'll walk through real quick some of the prereq stuff here on creating that cluster. Once you're in Google Cloud and you're on your main console page, you'll go up to the top left to that navigation menu or the products and services menu, head on down to Marketplace, and you're going to search for Fluid Slurm GCP. And just go ahead and click that top one there. This is just a CentOS based cluster, and then you'll go ahead and hit launch. There are some basic configurations here. I'm not going to go through the details today. You can use the default settings for just about everything. What I would recommend, though, is down on that compute node for the Slurm default compute partition. Click that drop down, scroll up on this second menu, the second sub menu here, and just change that to N1 standard 2. That way you're not spinning up really massive compute nodes. And once you're done, hit deploy. And that should get you started with your first, if this is your first, auto-scaling HPC cluster on Google Cloud. And you should arrive at a deployment manager page that looks something like this. Before this tutorial, I had already gone through and created one. Once your cluster is set up, you'll see a page that looks like this. It's got your login node's IP address. So if you want to SSH in with third-party tools, you'll have to do some additional work to use OS login to SSH in with like OpenSSH. However, you can just use the SSH button on the console here, which will open up a terminal in your browser. All right, so that's really it on the prereqs. If you're following along and you need an HPC cluster to experiment with as we're going through this tutorial, that's how you do it. And I'm going to go ahead and open up the Compute Engine UI. So if you didn't catch that, what I did is go to the Products and Services menu. You can scroll down to Compute Engine underneath Compute. And you should have a login and controller. Again, those IP addresses are there. I'm going to go ahead and copy my login node's IP address. So let's talk real quick. Now that we've gone through the prereqs here, you've got a cluster, you're on Google Cloud. We're going to do a few different things today. So we're going to look at 3 different strategies for managing Python packages. And I've categorized them in these 3 groups, what I call centralized, decentralized, and containerized. The centralized approach essentially is going to put you in a space where you're managing, where you have maybe one user or a group of system administrators that are managing Python packages for everyone who's using the system. And you can do this with an environment modules loaded Python that we've provided for you on this particular cluster. Now, if you're on another cluster at your home institution, if you want to do something like this, essentially the idea is to have Python installed on an NFS mounted location. On our system, it's a directory called apps that gets mounted to the login node and mounted to all the compute nodes. And then we use environment modules to bring that version of Python into our path. So we'll talk about a little bit of the strategy there on how you'd manage packages and what that ends up looking like for your users and for system administrators. And then we'll go through the decentralized approach, where we'll walk through how to use virtual environments. This is kind of nice for software developers sort of take on that responsibility and have a little bit more control over the packages that are available. Virtual environments essentially gives developers a way to manage their own software dependencies in Python in their home directory. So you don't need to go root to do any of this. So it's a pretty nice strategy. And now the third option is the containerized approach. And this is by far one of my favorite approaches, simply because it applies more to more scenarios than just Python applications. You can use this for Fortran applications, C application. I mean, you name it, you can containerize it, and then we can actually deploy it on an HPC cluster. In our case, we're going to talk about how to do this with Cloud Build and Docker to create Docker images of a Python application and then launch them on an HPC cluster with Singularity. So again, on our cluster that we're demoing here on Google Cloud, we have all these tools available to us right away. If you're doing this with on-prem, you'll want to have Singularity installed locally and then have some way to interact with a Docker container registry. So with that in mind, if you're following along, let's go ahead and get started. What you're going to want to do, if you want to use the code that we provided for this tutorial, you can go to GitHub. Under our Fluid Numerics GitHub page, you'll find a Fluid Slurm GCP demo, Python demo repository. And this has some very simple code in it. You're going to want this in two locations. You're going to want a copy of this on your local system, and then you're going to want a copy on your HPC cluster. If you're following along with the demo today, you'll need it in both spots. So I've already got a copy here on my local system. If you can see down on my terminal on the bottom. I'm also going to go ahead and let me go ahead and grab that IP address, and we'll go ahead and hop into the login node and get that installed there. Okay. All right, so I'm going to go ahead and just run that git clone command real quick to get myself set up on this side. Okay, pretty straightforward. Let's go ahead and check out what's going on inside this repository. So there's a few files that we have here, and we'll get to them as we go through each of the methods for managing Python application dependencies. So we got a cloud build.yaml and a Docker file. These are going to be primarily used for that containerized approach. If you did want to have, if you needed a script to install Python 3 on a non-standard location, we've included a script there for you. So if you're doing this on your own HPC cluster, let's take a look inside there, right? All it's going to do really is download the source code for Python, build it using their autoconf system, and create a module file for you. So it gives you a good jumping off point if you want to set this up on your own. We also have some batch files. So these are Slurm batch files that we'll use to submit various jobs to run our application here, which is just test.py. Let's take a look at that guy. Test.py essentially is going to import SciPy, NumPy, and Matplotlib, and then it's just going to print out to screen the version of SciPy, NumPy, Matplotlib, as well as the location of those packages. And the reason why we're doing this for this demonstration is because as we change each approach, the location of those modules those dependencies are actually going to change depending on what approach we're using, and it's going to help illustrate to you guys how this is actually working. So that's really it at a basic level. If you did have your own Python application, you could certainly be following along with some of the steps we're doing here with your own application. Okay. So yeah, let's go ahead and just get started. Let's first talk about the centralized package management. So on most HPC clusters, you will typically have like a home directory and then some other set of directories that are NFS mounted from like a central file server. And if you're using the Fluid Slurm GCP cluster on Google Cloud, we have really three locations, but etc you're not really gonna be doing any reading or writing from. That's just a requirement for Slurm there. But really, we have home and apps. Both of these directories are NFS mounted from the controller node, which hosts the Slurm job scheduler. That server will serve out the apps at home directory to login node and to any of the compute nodes that get spun up as we submit jobs. So it's important that whenever you install packages for Python, you don't want to use the system install for Python. So what do I mean by that? If I were to run which Python, or even which Python 3 and which pip 3, okay, you can see that these are all referencing user bin. But user bin is a local directory right now on the login node. And what this means is if I spin up another VM on Google Cloud, that directory on the login node, the login node's user bin, will not be available on any of those other VMs. Of course, if we decide to NFS mount it, you could, but that's not really a good thing to do with those root level directories. So what we've done is provided environment modules. Okay, so if you run module avail, you can see what modules are available. You can see we've got Python 2, Python 3, and a Singularity 3 as well. And if you were to look underneath the apps directory, you'll see we have the various versions of Python available underneath apps. And the nice thing about that is since they're installed under apps, any application that wants to use those particular versions of Python and any of the packages installed with them, those can be accessed from the compute nodes simply because apps is NFS mounted. Now, the caveat here is if you're doing the centralized package management, typically some of these directories where HPC packages are held are controlled by system administrators. And if you're running your own HPC cluster on Google Cloud, this is a decision for your organization to make, is how do we want to handle our package management? Do we want to have a team of system administrators that kind of take care of making sure all the packages are available for our researchers, or how do we want to do this? So all I'm going to do here is just walk you through these three approaches. Let's go ahead and get started. I'm going to go ahead and go root, since the apps directory requires root in order to write to it. And then we'll go ahead and module load Python 3.8.2. Okay, so now if I run which Python 3, you'll see that it's actually now pointing to this Python underneath apps, which is good. That's what we want. And if I run which pip 3, this is going to also point to a pip 3 underneath apps. So whenever I install packages with pip 3, it will end up placing those packages underneath apps so that they will be available for those compute nodes. So let's go ahead and run pip 3 install. Let's go ahead and put our packages in there: matplotlib and numpy. Okay, so it's going to take a minute to go ahead and install those. What we're going to do next, once these packages are ready to go, we're going to run our test application, test.py, using a batch script. Now on our cluster, you notice that in the Compute Engine UI, I still right now only have two virtual machines, a login node and a controller. You might be asking yourself, where the heck are those compute nodes? And if you didn't check out the live stream we had a couple weeks ago, basically, the way this cluster works is that the compute nodes are created as needed. It's an auto-scaling cluster. So whenever I submit a job, if the compute node's not there, Slurm will create them. When the job's done, once the nodes become idle for 5 minutes, they'll be taken down. Okay, looks like our packages have installed. Let's take a look at that batch file we're going to use. So again, if you're following along, we're just doing the centralized package management here, and we're going to use test.batch to submit that job. First thing to notice here is we got two sections of this code. So the top part is basically, the Slurm batch files are just bash. They're shell scripts, except they have this header information where you're basically putting in commands for Slurm, or in this case for the Slurm sbatch command. If you have Slurm accounting on your system, and certainly if you're using the Fluid Slurm GCP cluster, you're likely using Slurm accounting. Just make sure that you set the account to the correct Slurm account that you've configured, and make sure you set the partition to the correct partition. Now down below we have the actual steps we're going to execute. When we start the script, what it's going to do is it's going to purge out any modules that may have already been loaded on the compute node. We're going to load Python 3. We're going to just report to screen which Python, and we're going to run our test application. So let's go ahead and do that. Whoops, I am root. I should not be root and trying to submit jobs. So let me exit out of root and try that again. Okay. Nope, that's not my name on this system. There we go. Okay, so right now we've got a job running in the demo partition. Okay, and the status is configuring. Okay, and it's going to run on demo partition 0. I'm going to go ahead and refresh my Compute Engine UI, and you can see now I've got a demo partition 0 node. Okay, so if I check back here, it's still going to be configuring, and the reason why that is, so in the background, what's actually happening is the Slurm controller issued some commands to Google to create that instance, and it's using it's launching that instance with a virtual machine image that we've already created, and that has things like the Slurm daemon and some other tools set up so that it like auto mounts home and apps for you. All those things are already available, so you don't have to worry about it. That whole process to start up and basically wake up what's called the Slurm daemon and get it to communicate with the controller can take, you know, generally between 30 seconds to like 2 minutes. It's variable, and it depends on your usage, depends on time of day, what zone you're in. A lot of different factors come into play here. But it's really not too long. You can think about this like your queue time that you might have on your on-premise resources. Our job did run, which is nice. So the output for these files, I should have pointed out when I was in test.batch, the -o and -e flags basically say, take the standard errors, take the standard output, and put them in a file called test.out. So if I look at test.out, okay, we can see that it's reporting, hey, it's using apps Python 3.8.2. It's using, it's basically referring to SciPy underneath that same location, underneath apps. So this is exactly what we wanted. And again, the way we're making those packages available is just over an NFS mount. But because we required root privileges, this might not be an ideal workflow for every organization. So let's look at the next route. So decentralized package management is a way to basically put the control of package management in the developer's hands. And we're still going to use that Python 3.8 module because we've set that up where it is installed with virtual environments. Basically what's going to happen here is when we create a virtual environment, it's going to basically duplicate the Python directory structure. So when we call Python 3, when we call pip3, it'll actually be referencing those in our home directories or wherever we make this environment directory. And when we install packages, it'll all be placed under there. So the first thing you're going to do as yourself, you don't need to go root, is module load Python 3.8.2. If you do a module list, you can confirm that module is loaded. And again, which Python 3 am I using? And which pip3 am I using? They're all underneath apps. Now the cool thing here is if I run Python 3 -m venv for virtual environment, env, what it's going to do is create a directory right here called env, and it's going to, like I said, duplicate that Python directory structure underneath. So give that a minute to create. Wonderful. All right. Let's go ahead and to activate this virtual environment, to make it the thing you're going to be using, just run source env bin activate. Okay. So now if I run which Python 3, now it's using Python 3 underneath my home directory. In fact, it's the one installed underneath env in this current directory. And if I do, again, which pip3, no surprises, right? It's underneath our home directory. And the nice thing here is because I'm doing it in my home directory, the home directory is mounted on those compute nodes. All is good. So let's run a pip3 install scipy matplotlib numpy. Let that go. And I'll add, while we're waiting for those packages to install, if you have any questions during the tutorial, if you subscribe to our channel, you'll be able to hit the chat window there and ask us questions, and I'll do my best to answer them as we go here. So let's see here. Still got a couple more seconds to go here on that install. But essentially we're going to do the same thing as we did last time. Okay, we're basically going to run another batch job. There's another batch script for that. It's called test.venv.batch. It's going to do the same thing as before, except this time what's going to happen is it's going to have to activate that virtual environment on the compute node. So let's take a look at how that works. So if we open up test.vnv.batch, again, make sure your account and partition are correct if you're following along. Okay. Still going to do a module purge, module load for Python 3. This time, before we run the job, before we run the application, we're going to run source env bin activate, so it activates that virtual environment, and all those packages end up becoming available. If I do which Python 3, right, it's going to tell us which Python it is. Should be the one underneath our home directory in this env path, and then we'll run that test application again. So let's go ahead and run that. Cool, job went. And because that compute node was already live, we didn't have to wait for it to spin up. So the job went through right away. Okay, let me clear my screen a little bit. All right, so now you can see which Python? It's using home, Joe, FluidStorm, GCP underneath that env directory. Which SciPy, NumPy, and Matplotlib is using those packages underneath that env directory. So in this case, I mean, we were able to have those packages available, but we didn't need to go root. And this does put some more control into the hands of your developers, which can be very empowering to a lot of teams if they're able to actually have that kind of control. And of course, without having any I guess you don't really need to have the ability to go root to do this. So this does meet some, for some folks who want to basically control who has root access on a cluster. This ends up being pretty nice. Okay. So last approach here, we're going to be doing a containerized approach here where we're going to build a Docker container using Google Cloud Build. We're going to store that Docker container in the Google Container Registry, and then we're going to pull it into the cluster with Singularity and run it on the compute nodes. So to do this, we're going to go ahead and exit out of the login node, go back to your local system. Ideally, if you're doing this on your local system, you should have the gcloud SDK already installed and set up. If you don't, that's okay. There's a workaround, and the workaround is from your Cloud Console. What you can do is up on the top right, there is a button for Activate Cloud Shell. If you click that, this will open up a Linux terminal on in your browser. Let's go ahead and open it in a new window. Okay, and this will have the gcloud SDK already installed, already set up, and linked to your account. And you can it does have Git there, so you can actually clone that demo repository there if you're following along, and you can do all this work from there. It's a perfectly acceptable solution. For me, I'm going to go ahead and work from my terminal since I've already got it set up. Okay. So let's take a look here real quick at that Docker file. So the Docker file is essentially a recipe that says basically what you need to do to build your application. So we're just starting from Python 3.8.2, a container image that has Python 3.8 in it. We're going to pip3 install in that container. We're going to copy everything in the current directory on our host, on a system we're running on, into a directory in the container called app. So whenever I call the test.py application, it will have to be referenced to /app inside the container. All right. So let's take a look here. The next thing we need to look at is the cloudbuild.yaml file. This is we'll have in the future here some more episodes on how to really getting into detail with Cloud Build. But the short end of it is here, essentially we're defining a YAML dictionary that describes the build steps necessary to create your application. And here all we're going to do is call Docker to build the Docker file in the current directory, and then we're going to post the image to the gcr.io, which stands for Google Container Registry, in my project. Project ID happens to be an environment variable in Google Cloud Build that references to your current GCP project. So yeah, it's basically going to publish that container image to the Google Container Registry in my project, and we're going to call it Python demo Slurm GCP. Okay, so that's really it. Again, if you're let me run this command and then I'll finish my thought here. So to build this thing, you're going to use gcloud builds submit dot for the current directory. Actually make sure I'm in the correct project here, because I might not be. So let's say gcloud config set project, and I am on cloud. HPC demo is what I want to use. Now let's run a gcloud builds submit. Okay, so the way this works is, so Google Cloud Build is a service that provides an isolated environment for which builds can take place. And you notice that, you know, I can basically run all the commands I want inside that container image as if I was a user with administrative privileges. But it's all done inside that container. And that container is actually built in an isolated environment that you're not going to be able to access. It's highly secure. Cloud Build also has some really nice features associated with it. Like security vulnerability checking. So if you end up having like an application where you want to open up network ports and things like that, or if you're using certain packages, the Cloud Build tool has some security scanning features that help you just kind of make sure your applications are secure before they go to deployment. It's really nice. So I'll walk you through a little bit of the panel here while we're waiting for that build to happen. It looks like I did kick off 2 on accident here. But essentially go to that products and services menu, scroll down to your, I've got mine pinned up top here, but you might find yours down underneath tools. Yeah, underneath tools, go to cloud build. And essentially you have a few different views here. You have a dashboard, which if you have build triggers set up, this will give you a really nice summary of how well your automated application builds are working. Which again, if you want to learn more about triggers, tune in, I think 2 weeks from now, 3 weeks from now, we'll have some stuff on doing continuous integration on Google Cloud Build. So let's take a look at the history since I don't have triggers. Essentially, if you click through on the build that was active there, you'll get full logs of everything that happened. So you can see all the steps, right? We installed NumPy, Matplotlib, SciPy, and we created a Docker container. Where that ended up was in the Google Container Registry. So if you go down to Tools, you see Container Registry, and there's our container image. So if you click on that, now I've done this tutorial a few times now, so we have multiple versions of this container. Yeah, they're all here. And the nice thing is, so the container registry in the back end really is hosted on Google Cloud Storage. And which means you have really nice control on who has access to those container images using identity and access management policies. And by default, only people in your project with that with either editor, owner, or storage object viewer access can read those. So essentially, what we're going to do now is we're going to go onto the cluster. And we're going to do we're going to configure Singularity so that it can use the credentials of the service account on that instance to pull that container image. Now, if you're on an on-premise system, this is where it gets a little bit. You have a few extra steps you might need to do. The recommended approach is to create a service account on GCP and create a credentials file, a JSON credentials file for that, and put that on your local system. And if you have questions about this, feel free to reach out and I'd love to walk you through it. But essentially, you're going to end up using a service account on your own local system to be able to pull in that Docker container. Okay, so let's go back. I'm going to hop in my terminal here and we're going to SSH back into that login node. Okay. And we're going to load Singularity. And let's go ahead and use the gcloud SDK to configure a credentials helper, which will help this virtual machine handshake with the Google Container Registry. Go ahead and hit yes. All right, and now we can do a Singularity pull. We're going to tell it we're pulling a Docker image, gcr.io/, and you'll want to fill in your project ID here. Mine is Cloud HPC demo. So let's say Python slurm, Python demo slurm GCP, and we'll go ahead and pull the latest. Okay, so what's going to happen here? Maybe I didn't spell it right. Yeah, it's not an underscore at the end here. Okay, so what's going to happen here is Singularity is going to take that Docker container and it's going to convert it to what's called a Singularity image file. So for those of you who are not aware, Singularity is a container platform that was really meant for HPC use cases. So it naturally supports integrations with MPI or even bringing in device files for GPUs. Which makes it really, really nice. It's so easy to use for those platforms out of the box, especially if you're doing large MPI jobs where you're going across multiple virtual machines, or you're going across multiple compute nodes, especially when you're integrated with the job scheduler like Slurm. Singularity is it's made for this environment. The other benefit of Singularity over Docker on shared clusters, like an HPC cluster, is that you don't need root escalation to run your application. Now, if you were to build a Singularity container directly, you do need root access to build Singularity containers directly. But the approach we're taking here of using Google Cloud Build is essentially it allows your developers to develop on their own systems. It could be, I'm using a small Meerkat, just like an i3 chip on there, a little bit of memory, and maybe a terabyte of space. It's a nice small workstation. I could do a lot of my work there, do a lot of my build testing there, but then I used Google Cloud Build to actually do the full builds of my application and do a lot of my run testing using a Slurm cluster, actually. So in that whole process, though, I'm on a safe system. I don't need to be root, and as long as I have access to Google Cloud Build, there's no real need to ever escalate to root privileges. Everything ends up being really safe. And then when you end up going to run your application, if you're using Singularity, the need for root privileges to run a container is not there. Okay, so it looks like our Singularity image is done. We do have one other batch file for this. Looks like I did make that in my home directory, so I'm going to go ahead and move that Singularity image file underneath our repository. Okay, so we have one other batch file here. It's called test.singularity.batch. Okay, again, make sure that account and partition are correct. Now what's going to happen here is rather than loading Python, we're going to load Singularity. And instead of just running Python 3, we're actually going to run all of our commands inside that container. So you'll do Singularity run, give it the name of the CIF file. In this case, this is the Python demo Slurm GCP latest. We'll run which Python 3, and that's going to run, again, inside the container. So it's going to reference user local, but that's user local inside the container. It's kind of that whole directory structure is moving around with this application. And then when we run Python 3, now I have to run test.py underneath that directory app because the Docker file basically set up test.py underneath app inside the container. So let's go ahead and run that job. Okay, again, I've never gone root, which is nice. I'll refresh this screen here. We should see a compute node. Yeah, I think we waited more than 5 minutes between submitting jobs. That compute node was torn down. Now it's being created again to be able to run this job. So we'll give that a minute to go. I guess I do have a story I could fill in with here. For our applications, and this is kind of to build the vision for you of where this could go. We, like I said, develop a lot of our applications locally. One of them that I could talk about is Self Fluids. It's a multi-GPU fluids application, which, when in terms of testing, it's one of those applications that you need 8, 16, 24 GPUs in order to find sorts of bugs you would see in production, which most continuous integration platforms they don't provide access to that kind of resource. So the deal is, if we end up using Cloud Build to create our Docker containers, and we have a controller that sits there on standby and is ready to run tests. So Cloud Build ends up basically orchestrating this whole thing where the containers are created, and then the from Cloud Build, you can actually reach this Fluid Slurm GCP controller to submit a job and do a whole bunch of run testing. I mean, for us, we've got an application with it's like 96 core routines in there, and in each one of those routines, we have to exercise in a various number of ways, changing the number of MPI ranks, whether we're running on GPUs or not running on GPUs. I mean, if you're an HPC, you know the kind of portability issues that you're always thinking about. It is nice to have those automated. So at the end of the day, all told, we're looking at having thousands of tests that need to be run, and it's just unreasonable to think that we can do this manually. So all that stuff gets done basically based on build triggers in Cloud Build. So basically, we can just code it up, push it to the repository, and let Cloud Build return to us whether or not the build and run tests actually passed. We get full detailed logs, and we actually ended up doing something I thought was pretty neat, was dumping a lot of the results out to Google Sheets and then using Data Studio to visualize our application's performance, error convergence rates, things like that. If you're interested in seeing that, check out selffluids.com. We have a nice dashboard there you can play with. Let's take a look at what's going on here. And let's check our job. Looks like our job ran. So if I run test.out, so you'll notice you might see these warnings in here. Essentially, if you don't have group ID alignment inside the container and on the host system, you'll see these warnings. Don't worry, they're benign. But which Python 3 is it using? Well, it's actually using the Python 3 in user local. But remember, that's user local inside the container. That's not on the host system. Which SciPy, NumPy, Matplotlib, again, it's underneath user local, but those are packages that are inside the container, not on the host system. So I hope this was helpful for you. I mean, we gave you 3 different strategies to manage your packages. One is a centralized approach. It means you need a system administration team that handles package installations underneath an NFS-mounted directory that all your users can use, and it's available across your compute nodes. The other 2 approaches put more control in the developer's hands, which again can be very empowering for a lot of teams. It doesn't require root privileges, so this can all be done safely and securely. And first one was virtual environments there. And this last one we just showed was the containerized approach, where we're using Google Cloud Build and a container registry and linking that up with our HPC cluster to launch those applications. If you need any additional help, we have actually all the stuff we did today is available as a code lab on our site. So if you think this might be useful for your colleagues, certainly send them over to help.fluidnumerics.com/slurmgcp. Underneath that page, you'll find code labs, in addition to a number of other help documents on getting started with HPC on cloud environments, if that's the direction you're thinking of going. Of course, if you ever need help with using our clusters or any of the stuff we've talked about today, you can always reach out to us at fluidslurmgcp@fluidnumerics.com. We're standing by ready to help you get started. Thanks again for joining. If you want to find out more about what we're doing, we do have our live stream schedule posted on our website. And we do these every Thursday at 4 p.m. Mountain Time, Fridays at 9 a.m. So we try to fit a little bit of both the evening and the morning schedules for y'all. Thanks again for joining. We'll be doing this one tomorrow. So if you know of some colleagues that would enjoy learning about Python package management on HPC systems, send them our way tomorrow morning. Next week, we've got up in the queue for you how to build and run a custom VM image that has OpenFOAM in it on Google Cloud. So I hope you guys tune into that. Thanks again for joining, and we'll see you next week.